All right, welcome back. Today is November the 2nd, and so we're going to start a new chapter, chapter 9. Now, I don't know if you will notice on my recordings that I was using version 7, which is the previous version of the book that we have currently. This is version 8. In version 7, they split chapter 9 and 10, and in version 8, they merge it. They merge substitution reaction with elimination reactions. So the only thing you have to worry about is that when you see the first slide of chapter 10, that is actually still part of chapter 9. All right? It's the only thing, because I have it linked so that it says chapter 9 for you. All right? And then your chapter 10 is chapter 11 here, and chapter 12 is chapter 11, chapter 13 is chapter 12, like that. So it's a little. I try to edit it with YouTube, but I didn't know how to do it. So sorry about that. I spent like 2 hours figuring it out, and I just couldn't do it. And then I had to buy a new software, which I didn't want to. Okay, so that's why I labeled this chapter 9A, part A. And on my slides, I have, for elimination, I have labeled them chapter 9B. All right? Okay, so I was planning on doing a quiz on chapter 8, but we're already done with that subject, so we're going to move on. We don't have that much time. There's only 3 weeks left, and each quiz takes half of the class, and I cannot afford it, which I was trying to do 6 quizzes. We ended up doing 6 quizzes, but one will be in class next week, and it will be on chapter 9. And another one, and I'll tell you when it will be. And then I have another, and then we'll have milestone 4 on the 20th in 3 weeks. So what I'm thinking is giving you maybe an extra quiz where you can knock off one of the smallest scores. But it will be a take-home quiz when everybody's at home. Hopefully on that Monday when we're off, the first Monday. And then you do it on your own, and I'll know that you'll be by yourself doing it. So I won't be proctoring you or anything. You just go in there and do the quiz and try to improve your grade. So that's the plan. That's the plan. Because I cannot afford doing 2 quizzes and an exam and cover all the chapters that I need to cover. All right. So I hope you like that idea. So I don't think. Let's see. Someone is saying something in the chat. Feel free to speak up. This is open forum here. Actually, I cannot even open the chat. Oh, there it is. Oh, you're welcome, Esther. All right. So, if I can just speak through this mask. All right. So let's talk about chapter 9. So I guess I'm gonna give you a little walkthrough, because I don't think you have seen my videos yet. I posted them yesterday. So we're talking about the SN2 reaction here. Is substitution nucleophilic bimolecular. The 2 stands for 2 molecules, of which one is the nucleophile, the other one is the electrophile. The reactions will not work without one of them. This is the second type of reactions in organic chemistry. These are nucleophilic reactions where your nucleophile is your Lewis base and your electrophile is your Lewis acid. It's still an acid-base reaction, but it's not the one with protons. It's the one that is with electrons. And so we're going to learn that the terminology here is that you have a nucleophile, an electrophile. The electrophile is the carbon that is partially plus, meaning it's the carbon that has the leaving group. And then the leaving group is a secondary product, after the reaction is finished. So you have a nucleophile hitting the electrophile from the backside. It's a backside attack with 100% inversion of configuration. Basically, imagine that you have an umbrella and the wind hits the umbrella and it flips it. And that's how you get the inversion of configuration. So if you have an R group, if you have a chiral carbon involved in the new SN2, you'll go from R to S, or vice versa. All right. The rate determining step is the slowest reaction step. In this case, there's only one step, and this step is concerted, meaning the electrons are attacking from the nucleophile at the same time that the electrons from the leaving group are leaving. So basically you have what is called bond making right here and bond breaking. All right? And it happens simultaneously at the same time. All right. So this slide here shows you that if you have a chiral carbon, you will end up with flipping from S to R. And so if you had, like, for example, notice that level rotatory and dextro rotatory doesn't get affected by the R or S. Those are independent. Here you have S minus and you end up with R minus. So the only thing that changed was the Kahn-Ingold prelog representation of the molecule with R or S. All right. So on this slide, I talked about using Fisher projections on SN2 reactions. Here you see the nucleophile is a nitrile group, the nitrile attacks on the backside where the bromine is, and that's gonna, or the chlorine, and it's gonna kick them both, and the hydrogen gets flipped from the push, because at some point you'll see that the transition state is such that, where is it? Right here. The molecules start getting flat. So it's like you have the three groups that are going to stay. In this case, it'll be the methyl, the C6H13, and the hydrogen. Those are on the same plane. And then the OH is going to take the place of the bromine, but on the opposite side. And so what I'm saying is these three groups are actually on an sp2 plane of symmetry. So it's almost like when the bond breaking, bond making, and the bond breaking is happening. The other three groups are flat. All right. All right. This shows you the mechanism of the SN2 here on a potential energy. So notice that that here's your nucleophile, your electron rich. This carbon right here holding the leaving group is your electron poor. And so here is the attack. Notice that the three hydrogens here are actually on a plane, and then the bond breaking and the bond making and the bond breaking is happening in the transition state. Then that gives you product once the bromine is kicked off. All right, so for this reaction, the transition steps, we know they are imaginary, and this reaction is only one step for the SN2. And so one thing you have to, and that represents that there's only one step on that reaction. And then for the SN2 reactions, there are 4 factors that you need to know. And we're gonna go in good detail talking about these 4 factors. The first one is the nature of the leaving group, the reactivity of the nucleophiles, number 2. Then the third is solvent, and fourth is the structure of the electrophile. All right. So here I talk about the nature of the leaving group. I explained to you and grouped them in excellent living groups versus moderate to poor to extremely poor living groups. The bottom line is, what makes a good living group? Well, it's their good living groups are weak bases. Notice that in the case of the extremely poor living groups, or even the poor living groups, those are strong bases. So if you have a strong base formed in the solution, guess what? It's going to react. That's why it's a poor living group, right? And also, something like with a carbon, that's never going to leave as a living group, never. Carbon is a very strong covalent bonded to another carbon in most cases, so it's not going to happen. Then I tell you something about a little bit extra about living groups. Here you have the tosylate, the mesylate, and triflate. They are part of the same family. They come from the family of the sulfuric acid, where you have a sulfur, in this case two oxygens that are double bonded and one that is not. So I believe this group is called sulfonate, the sulfonate group. And so basically, here I'm just telling you, hey, these are really good living groups that we use for synthesis. I'll give you an example here of choose the order, which one is most to least reactive, and you can see that the bromine is better. Then the second one will be the carboxylate, and the third one will be the hydroxide. The hydroxide group is the OH, is a bad living group. It only works when your media is basic. When your media is with a pH of over 10, that is basic. Your media is your solution in the reaction. If your reaction solution is basic, that is the only time where the OH could act as a good living group, because there is a driving force. Meaning, think of it as, okay, you already have OH in solution, and you're kicking off OH to put it in the solution. You're still putting more OH into the solution. You see what I'm saying? That is the only time when the OH group is a good living group. And a lot of students have trouble visualizing this phenomenon. All right. So I just covered the living group, the nature of the living group. We went here. Nature of the living group is the first factor. Then we're going to talk about the reactivity of the nucleophile. So this is the second factor, the reactivity of the nucleophile. Within itself, there's 5 things that you have to consider. Charge. You're going to see that we're going to talk about charge in the nucleophile. It's important to have a charge for the SN2. Basicity, the more basic, the better it is. Also, we're going to talk the effects of solvent. The solvent for the SN2, it prefers to be polar aprotic if possible, but it can still work on polar protic solvent, and I'm going to explain that in a second. And then you have the steric effects on the nucleophile, so you're going to see that if a nucleophile is bulky, it will not be a good nucleophile because it's too big. But if it's small but strong, it can do the SN2. And then we have polarizability. Polarizability is the how can I explain this? Is when a molecule can switch its electrons and go from one pole to another one. So it's going from like positive to negative, or rearranging the electrons so that it becomes more negative in one area. Let me give you an example of polarizability. For example, when this is a dipole dipole example. Say, for example, when you rub your hands and you grab a wrap of candy, the candy wrap is gonna stick on your hand, and you try to get rid of it. You try to get rid of it, right? That is because all the electrons rush from one end of the candy wrap to another side of the paper, and so that all of those negative charged electrons can then combine with the positive charge in your hand. That's why that is a case of polarizability. All right. All right. So for this strength, you'll see that the stronger the charge, the better it is, because the nucleophile, if it's charged, is going to be better than its neutral component. For trend of basicity, the more basic, also more nucleophilic. Electronegativity, nucleophilicity also decreases from left to right in the periodic table following the increase of electronegativity from left to right. So this is something that you have to now put in your long-term memory when we're comparing, for example, hydroxide to fluoride ions. Remember, the fluorine is the most selfish element there, so it's not going to be a good nucleophile, and that's why I have it here as an exception. Fluorine, when compared to the other halogens, it's a typically extremely poor leaving group, which forms strong bonds. All right. Then we're going to check out the reactivity of the nucleophile. Let's see. That is because if the nucleophile is charged, it'll be a stronger nucleophile. Then we'll look at steric effects. So, for example, in the case where you compare T-butoxide with etoxide, your T-butoxide has 3 really bulky groups like that. It's going to impede this negative charge on the oxygen to get through sterics when doing the SN2. Whereas something small like the etoxide is small, so it's kind of skinny but still strong. All right, and it can go and do the nucleophilic attack. So that is a case of steric hindrance for the case of T-butoxide. So choosing a less hinder base can make the attacking easier when you're performing an SN2 reaction. We're also going to learn that T-butoxide is good for E2. All right, so this is one of the things about these 4 type of reaction we're learning, which makes it really difficult to master. The SN2 competes with the E2, and the E2 beats the SN2. The SN1, on the other hand, competes with the E1, and the SN1 beats the E1. There's only a few cases where we can choose the E1 to be the major reaction, and that's when we use strong dehydrating acids like phosphoric acid, sulfuric acid. We're going to see those examples. But the SN1 usually beats the E1 product. All right? You're always going to have them. You're always going to have a mixture of SN2 versus E2 products or SN1 versus E1 products. All right? You following? So that's why those 4 compete and makes this chapter the most challenging chapter this semester. If you can pass this hurdle, I mean, you'll be home free pretty much. All right, you're almost there. 3 more weeks, just hang in there. All right. Then here we're going to talk about, what was that here? Oh, this is the effects of solvent. Notice that the solvent plays a role in swamping the nucleophile. Also here, this shows you the steric effects. Notice this is your T-butoxide group. There's too much steric here between these groups to get to this bonding orbital on the electrophile, so makes it really difficult for it to get through, and therefore the activation energy for that reaction will be really high. Sometimes too high that it will not be able to overcome it. Well, if your nucleophile is small, it could penetrate the sterics of the molecule that is attacking, and it does the SN2. All right. And notice that the solvent is everywhere, so it's swamping the reaction. So that's also going to take a major role. Okay, so here's the example of polarizability. So notice that you have fluorine versus iodine. We say that iodine is a soft polarizable atom, or ion in this case, when compared to the fluoride. And it's because now the iodine has more shells, electronic shells, and so it can touch the bonding orbital of the carbon that is the electrophile, allowing for it to do the SN2. It will kick out that bromine in that case. Fluorine is not as polarizable. Fluorine tightens those electrons closer to its nuclei, and it doesn't want to share them. It just wants, it doesn't want to do anything other than get. It doesn't want to share. It wants to get electrons. All right, so there's little bonding on the non-polarizable ions. All right. What is in here? A little bit more trends on nucleophilicity. All right, let's talk about solvent effects. So solvent effects is we're still here talking about the nucleophile, the reactivity of the nucleophile. So we're in solvents. So in solvents, you're going to notice that there are two types of solvents. One is the polar protic, and the other one is polar aprotic. So in your polar protic solvent, you have a proton. That's why it's protic, because it has a proton, right? So, and it's polar because it has a dipole. All right. So in this case, the molecule of water is bent. So you have a dipole going this way and another one going this way, and an overall dipole going that way, right? That makes it polar. The dipole makes it polar. But it also makes it protic because it has an H, has a proton that can be donated, right? And that H is right here next to the oxygen. That makes it protic. Alcohols are protic. They have an OH. So also the protic, these protons here, the protic solvents can donate that hydrogen. So that hydrogen, that proton is called exchangeable. It's an exchangeable proton because it could be loose, it could be regained. So that's why they are polar protic. Acetic acid also and amines are part of polar protics. So polar aprotic, these molecules are polar again by Vesper theory, where you have vectors. You have vector for this one. You have vector going from here to here. No, sorry, here to here. Oh, I already have it here. Let me erase that. And an overall vector going to the oxygen that makes it polar is aprotic. Why is it aprotic? Can you see it? Notice that all those protons are attached to carbons. This is the formamide has an CH. The DMSO, dimethyl sulfoxide, have also CH protons. Acetonitrile has CHs, and this other HMP has CHs. Acetone 2, diethyl ether, and tetrahydrofuran, THF, they all have CHs. and those protons are not exchangeable. So these solvents are polar aprotic. They don't give out that proton. All right. Check the SN2. Check out this reaction. We have this A side as the nucleophile is going to attack here and kick off the bromine to make that. And this reaction was tested in 5 different solvents: methanol, water, DMSO, DMF, and acetonitrile. And notice that the reactions still work a little bit with methanol and water. Those were polar protic solvents, but with polar aprotic, boy, it just took off, right? The rate increased tremendously. All right, up all the way to 5,000. It's over 5,000. All right. All right. So that talks about, that's all that covers for the nucleophile. All right. And so now we're going to talk about the third factor, which is, we talked about solvent. Never mind. So we already talked about 3 of them. Now we're going to talk about the structure of the electrophile. All right. So that's the 4th factor. All right. And all these factors you will learn by doing problems. All right, check this out. So here is the 4th and final factor of the SN2. We have methyl groups, we have primary alkyl halides, secondary, tertiary. Notice that the SN2 reaction increases towards the left, where there's less sterics. All right, you see that? So methyls, primary alkyl halides undergo SN2 reaction with ease. Secondary alkyl halides react more slowly. Usually they make elimination products, E2 products. So when you are in that situation, it usually prefers E2. E2 will win on a secondary alkyl halide. Which kind of is hard for us to generalize second, but I'm going to have to do it as a general. You'll notice that we're going to say here that methyl is better than primary, better than secondary, better than tertiary, because with tertiaries there's no SN2 reactions, and with secondaries there's competition. All right, but we have to generalize that. So when I give you a table at the end of this talk, of this chapter, I'll give you a table, and I'm going to try to generalize things. Let's take this as a grain of salt, because the secondaries are usually going to be making E2s, all right? But we have to mention them here. Are you guys clear with that? All right. So notice what's happening here. So they took ethyl chloride on this slide and made it the benchmark. I call it the benchmark because it had a relative rate of 1. So they had to start from somewhere. And that was the beginning. Then when they compare that to the methyl chloride, the relative rate was 30. All right, so it reacts 30 times faster than the primary. So methyl chloride is a methyl alkyl halide. Ethyl chloride is a primary alkyl halide. How do I know it's primary? So, hold on. Give me a second. All right, yeah. So how do I know it's primary? So the carbon in blue here that is holding the leaving group only has one neighbor carbon in black. That's why it is primary. All right. So propyl chloride is also primary. Butyl chloride is also primary. Then we go to isopropyl chloride. Notice that the rate is decreasing already to 0.025. And why I know it's primary, I'm going to repeat it again. The carbon holding the leaving group has 2 carbon connections as neighbors. So that makes it secondary. All right? That's how you're going to do it. And then tertiary is T-butyl chloride. The carbon holding the leaving group has 1, 2, 3 carbons in black here. These are the neighbor carbons for that blue carbon. So it's tertiary. It has 3 neighbors that are carbons. All right. So notice that also sterics plays a factor here. Neopentyl is primary because the carbon holding the leaving group only has 1 neighbor, but that neighbor has 3 methyl groups, which is not part of being primary, secondary, tertiary. It's just being part of sterics. And so for a nucleophile to do the backside attack on this carbon in blue to get rid of that chlorine, it's very hindered. It's like having a few bouncers, outside a building. You got 3 bouncers there, and so it's kind of hard to get rid of that chlorine. All right, so it's primary, but notice that the rate slowed down because of the steric. So all those factors need to be taken into consideration. All right. All right, I've talked a lot. Any questions up to this point? No questions. All right, if no questions, better, because I can move on. All right, and we can finish this semester. How cool is that? All right. Then let's talk about this other comparison here. Ethyl chloride against the benchmark at 1. Methyl chloride is the little example that the methyl is faster than the primaries. Then they compare that to allyl chloride and benzyl chloride. And check this out. Benzyl chloride, boom, super fast, 120 times faster than ethyl chloride. And that is due to resonance. And also know that benzylic carbons, we talked about that, they are the most reactive species because of resonance. And also comparing benzyl chloride to allyl chloride, they're similar, you can say. One was 120, there was 140. Still benzylic is better than allylic. So how do you recognize an allylic? So an allylic is a double bond with a carbon, and then in this case the chlorine will go there. So this is allylic. This is, whenever you see this is a vinyl. So this is vinylic. It's a little different. All right, don't get confused with those. All right. So this one right here is that one, allylic. All right, and allylic is shown here. It's a good leaving group because it has resonance. Check it out. You can. This is a SN2 reaction, and if you're a little more advanced, when you get a little more advanced, notice that you can also do this. Nucleophile attacks here. This double bond flips there, and that gets kicked off, and you still get the same product. This is called the SN2 prime. We're gonna learn that. Usually we learn that in the second semester or in advanced OCHEM, but I'm just giving it to you right now. All right, this is the SN2 prime. It gives you the same product. All right, so it gives you a double bond and the nucleophile attached right there, like that. That's the product of this reaction, and chlorine is doing absolutely nothing in the reaction mixture. All right, so we get to the summary of the SN2, and by the way, I have placed, I think I have, no, I haven't. I will put this, now I have to like split this semesters. Important handouts. On the important handouts for you in Canvas, I will put this chart, which I try to generalize. All right, and you're gonna learn that this is all about what we're gonna be learning about SN1, SN2, E1, and E2. And here I have grouped them by cases and what they do, how they do it, and how they are more optimized. All right, so you will have this comparison chart in Canvas, so look for that. All right. And so basically that's going to be the summaries at the end of each particular section that I have here. I didn't add the temperature here because it was not mentioned in any of the other things. The temperature and all that, that's actually useful for reactions when we actually get to see the cases. But here we go. So the stereochemistry of the SN2 is 100 inversion of configuration. So you go from R to S or from S to R. The structure of the electrophile, benzylic and allylic, are approximately about the same in strength, followed by methyl, primary, secondary, and tertiary. The nucleophile, the SN2 prefers a charged nucleophile. The solvent should be polar aprotic, where there's no heteroatoms, so you don't have an OH or an NH or an SH. Those are heteroatoms with protic groups. Here you have pure aprotic groups. Then the mechanism is a one-step concerted reaction where the bond making and the bond breaking are happening at the same time. And then the kinetics is that the rate of the SN2 reaction is equals to rate constant times the concentration of the electrophile multiplied by the concentration of the nucleophile. So you need those two in order for this to work. Now let's talk about the SN1, and hopefully I have enough time to cover it all. I did it in the morning, so I should be able to, because I'm just walking you through this boulevard of slides. All right. We don't want to make it the boulevard of broken dreams, right? This is where dream starts, not where they're broken. The SN1 reaction, in this case, it stands for substitution nucleophilic unimolecular. The one stands for uni, for one. And the rate of the reaction is equal to the rate constant K times the concentration of the electrophile only. It doesn't matter what you do with the concentration of the nucleophile, you can increase it to 10 times. And if the electrophile doesn't make the carbocation, it doesn't go anywhere. So the electrophile has sole control of the reaction and is the rate determining step. All right? So the rate determining step is the formation of a carbocation intermediate. All right? So notice that for this, the SN1 is a funny reaction, I think, because the leaving group just leaves. It's like a kid that is like 18-years old and suddenly says to my mom, "Mom, I'm leaving the house." And the mom said, "All right, see ya." Now be okay. You go and pay your own insurance. And here's the mom right here. She becomes a carbocation. She's free from that kid. All right. So that is the SN1. It's just a kid that decides to leave home. And then a nucleophile comes in. The nest is empty, right? No, I need to stop there. All right. Okay. So the nucleophile comes and attacks the carbocation. Attacks the carbocation, and there you make the new product. All right, and yeah, this is the story of uh, carbocation. All right, the SN1 reaction, the end. Then you have two bumps here. You have you have two steps for this particular case, but you're gonna see that for the SN1 we can have multiple steps as long as we form that initial carbocation. All right. Okay. Uh, so notice also that the nucleophile for this reaction is the solvent. So in this case, it was a carboxylate, acetate anion solvent was the nucleophile. All right, so let's take a look at this other SN1 reaction. This is a better reaction, I think. So it's a story of 3 steps. So here we have Claire. Claire is the chlorine. She's a rebellious girl now. Let's change the story. She leaves the house. She leaves the house. Here's bond breaking only. For the SN1, it's basically bond breaking. All right, and then here's the so it forms the first intermediate is your carbocation, and that is the rate determined step. Notice that the energy of activation is tallest compared to the other ones. All right, so that is the rate determined step. Then the water is the nucleophile. So in this case, this will be hydrolysis because you are breaking a molecule with water. Hydro means water, and so notice that the approaching transition state is the water coming to be in contact here with the carbocation. Then it forms a product, and that product contains a molecule of water. That molecule of water needs to be free base. So another molecule of water comes, grabs this H, or the chlorine. Doesn't matter, it's going to form H3O+. That forms an acid, and that's shown here. And then that's another transition state where the hydrogen from the water molecule is leaving with the water to form H3O+, and then you form your alcohol. All right, so then you have 3 bumps or 3 humps, and that means there are 3 steps. All right, so you can explain the SN1 here. This shows here step 1 where you form the carbocation. Here's the carbocation intermediate. That is the most important step in the reaction. Without that, the reaction doesn't form. Also known that the carbocation is totally sp2 because it's flat. So if you were to make this into a nice round flat tortilla, it'll be pretty tasty. It'll be really, really flat. All methyl groups are pointing into different directions. That molecule is flat on the table. All right. Then I think this is steps 2 and 3 of that same reaction. I'll give you another example of an SN1 reaction with chirality now. This is a little bit different. Check this out. If you have chirality to start, you are going to end up with a 50-50 mixture of the R and the S. So here we started with the R. Then the bromine simply leaves. It just leaves. It's a mystery, but that's what it does. It just leaves. It's an ungrateful ion. And then water is your nucleophile. Notice that you have a combination of water and an acetone. Sometimes they do that just to test kinetics. But water is the polar is polar protic, right? Acetone is polar aprotic. One thing about the SN1, and you can write that down. The SN1 does not work with polar aprotic solvents. It only works with polar protic solvents. All right. So now you have your carbocation form here, and water can attack, as shown here on depicted as A and B. A is blue attack, B is the red attack. And so if it attacks on the top, it's going to retain its configuration because based on Can-Ingold pre-log, it's going to have that orientation, so that is R. If it happens to be from the bottom, that gives you the S. So that's going to be a 50-50 mixture. All right. All right. So I'm going to step on the pedal here. So solvolysis reactions are also known as SN1 reactions. So an SN1 is also a solvolysis reaction. It's broken by the solvent. This shows you an example of the relative rate of a reaction that was 100% water versus 10% water and 90% acetone. Notice that the rate decreased tremendously from 400,000 to 1. It says an SN2, notice what it says here, an SN2 reaction will occur in a polar protic solvent. However, it will react faster in a polar aprotic solvent. An SN1 reaction is very unlikely to occur in an aprotic solvent. So these little things are important to know. So the effect here is the opposite. So notice that it's faster, the reaction is faster on tertiary alkyl halides. So tertiary is faster than allylic, faster than benzylic, faster than secondary, and faster than primary. An SN1 will not actually work on a primary alkyl halide. And so if you give me 1 minute, I'll just finish the summary. For the SN1, expect that the stereochemistry will be 50-50 racemization if it's chiral or when it's chiral. If it's not, doesn't matter. The structure of the electrophile will be tertiary. It's better and faster than benzylic and allylic, faster than secondary, faster than primary. The nucleophile is weak because it's not charged. It's a solvent. It's a neutral species. And then the solvent should be polar protic. So you have acids, you have water, alcohols, amines, etc. The mechanism is multi-step. You can have 2 steps, 3 steps. We've seen it. And then the kinetics, the rate will be equal to the constant K times the concentration of the electrophile. I'm going to stop right there. Have a wonderful day, guys.